Type 1, a supernova. Type 1, a supernova are thermonuclear explosions that serve as the universe's most reliable measuring sticks. They occur when a white dwarf in a binary system steals matter from its companion star until it reaches exactly 1.4 solar masses, a threshold discovered by Subrahmanyan Chandrasekhar. At this critical point, the dwarf can no longer support itself and detonates in a runaway fusion reaction. The explosion is so uniform that astronomers use these as standard candles to measure cosmic distances. Peak brightness reaches about 5 billion times brighter than the Sun, taking roughly 20 days to reach maximum before fading over months. Unlike other supernovae, Type 1a explosions leave absolutely nothing behind. The entire star is obliterated. Their spectra show silicon absorption lines, but no hydrogen, revealing the dwarf's pure composition. These cosmic benchmarks helped scientists discover that the universe's expansion is accelerating. Type Yb supernova. Type Yb supernovae are the stripped-down versions of massive star deaths. These explosions begin with stars weighing 20 to 40 solar masses or more, but something happens before they die. Powerful stellar winds rip away the outer hydrogen envelope, leaving only the helium layer exposed when the core finally collapses. The collapse happens when the core builds up iron, an element that can't be fused for energy. Within less than 1 second, the core implodes, then rebounds in a catastrophic explosion. What makes Type 1b distinct is its spectrum, which shows clear helium lines but absolutely no hydrogen. The temperatures during collapse reach billions of degrees, and remarkably, 99% of the energy escapes as neutrinos, not light. These explosions leave behind either a neutron star or black hole depending on the original mass. The blue supergiant progenitors shed their hydrogen through intense radiation pressure over millions of years before meeting their explosive end. Type Yc supernova. Type Ic supernovae are the most stripped category of core collapse, having lost not only their hydrogen, but also their helium layers. These are the bare cores of once massive stars, typically requiring initial masses exceeding 25 to 30 solar masses to shed so much material. The most common progenitors are Wolf-Rayet stars, extremely hot blue-white giants with surface temperatures between 25,000 and 50,000 degrees Celsius. These stellar furnaces lose mass at an incredible rate, up to 1/10,000th of a solar mass per year through violent stellar winds. By the time the core collapses, only the carbon-oxygen core remains, which is why the spectrum shows neither hydrogen nor helium lines. Instead, carbon and oxygen dominate the spectral signature. The explosion mechanism is the same as other core collapse types, with iron buildup triggering the implosion. But the absence of outer layers creates a cleaner, more symmetric explosion. Wolf-Rayet winds are so powerful, you could see them stripping the star if you watched from a safe distance. Type Y CBL supernova. Type I CBL supernova, where BL stands for broad line, represent the most energetic standard core collapse events in the universe. The broad spectral lines come from material moving at insane velocities exceeding 30,000 kilometers per second, roughly 10% the speed of light. These explosions release about 10 to the 52nd ergs of energy, approximately 10 times more than typical supernovae. What sets them apart is rapid core rotation near breakup velocity, creating conditions for something even more spectacular. Many Type 1 CBL events are associated with long-duration gamma-ray bursts lasting 2 seconds or more, making them cosmic death rays visible across billions of light years. The rotation causes the collapse to form an accretion disk around a newborn black hole, driving relativistic jets that punch through the star's poles. These jets accelerate matter to nearly light speed, creating asymmetric explosions far more violent than their symmetric cousins. The collapsar model explains how rotation channels energy into focused beams rather than spherical expansion. Type 2 P supernova. Type 2 P supernovae are the most common type of stellar explosion, accounting for roughly 60% of all core collapse events. The P stands for plateau, describing a distinctive feature in the light curve where brightness remains nearly constant for 80 to 100 days. This happens when a red supergiant star, typically 200 to 800 times the Sun's radius, explodes while retaining its massive hydrogen envelope of about 10 solar masses. As the explosion expands and cools, hydrogen begins to recombine with electrons, releasing energy that sustains the plateau phase. Initial stellar masses range from 8 to 25 solar masses, and these stars live as red or yellow supergiants before their cores collapse. The explosion reaches peak brightness around 1 billion times the Sun's luminosity, lighting up entire galaxies. After months, radioactive decay of nickel-56 takes over as the primary energy source and the light fades. The remnant is typically a neutron star. Betelgeuse, the red supergiant in Orion, is a potential Type 2P candidate that could explode any time in the next 100,000 years. Type 2 L supernova. Type 2 L supernovae are the linear cousins of Type 2P, showing hydrogen in their spectra, but declining steadily in brightness rather than plateauing. The L stands for linear, describing how the light curve drops at a constant rate of roughly 0.05 magnitudes per day after peak. These explosions come from stars with similar initial masses to Type 2P progenitors, but with smaller hydrogen envelopes, typically less than 5 solar masses. The difference might result from enhanced mass loss during the star's life, possibly through stellar winds or binary interactions that stripped away some, but not all, of the hydrogen layer. Yellow to red supergiants serve as the typical progenitors, and they reach peak brightness in about 15 days. The thinner atmosphere means less hydrogen to recombine, so there's no sustained energy release to create a plateau. Some astronomers debate whether Type 2L represents a truly separate class or simply the low envelope end of a continuum with Type 2P. Either way, these explosions still create neutron star remnants and share the same core collapse mechanism driven by iron buildup. Type YIN supernova. Type YIN supernova, where N stands for narrow spectral lines, are the dramatic collision events of the supernova world. These explosions occur when the ejected material from a dying star slams into a dense shell of gas that the star expelled years or even decades earlier. The circumstellar material was ejected relatively slowly at 10 to 100 kilometers per second. But when the supernova ejecta, screaming outward at over 10,000 kilometers per second, hits this shell, it creates an incredibly bright shockwave. The narrow emission lines come from the slow-moving circumstellar gas, contrasting with broad lines from the fast ejecta. This collision is so energetic that Type 1 IN supernovae can be 10 times brighter than normal Type 2 explosions and can stay luminous for years, with some lasting 5 years or more. The progenitor stars are likely massive stars experiencing violent mass loss episodes before death, possibly luminous blue variables. The extended light show isn't from the explosion itself, but from the kinetic energy of the collision being converted to light, creating one of astronomy's most spectacular sustained displays. Type 2b supernova. Type 2b supernovae are the shapeshifters of the supernova world, starting as one type and transforming into another over the course of weeks. Initially, their spectra show hydrogen lines, classifying them as Type 2, but as time passes, the hydrogen lines fade and helium lines emerge, making them look like Type 1b. This metamorphosis happens because the progenitor star had a very thin hydrogen envelope, typically just 0.1 to 1 solar masses, barely clinging to the helium layer beneath. These stars begin with masses between 12 and 25 solar masses and exist as blue supergiants when they explode. The transition from hydrogen-dominated to helium-dominated spectra occurs roughly 10 to 20 days after maximum light as the thin hydrogen layer expands, cools, and becomes transparent. The most famous example is SN 1993J, which was extensively studied and confirmed the transitional nature of this class. The explosion mechanism is standard core collapse, but the minimal hydrogen envelope makes Type 2b a perfect intermediate case between hydrogen-rich and hydrogen-stripped explosions. Electron capture supernova. Electron capture supernovae represent a fundamentally different explosion mechanism occurring in a narrow mass range of 8 to 10 solar masses. Unlike typical core collapse, where iron buildup triggers the implosion, these stars have degenerate cores made of oxygen, neon, and magnesium that never reach iron formation. Instead, electrons get captured by neon and magnesium nuclei, removing the electron degeneracy pressure that was supporting the core against gravity. The core collapses despite never making iron. These explosions are weaker than standard Type 2 supernovae and produce unusually low-mass neutron stars around 1.3 solar masses. The ejecta contains unusual chemical signatures that hint at the unique mechanism. This type was theoretically predicted by Kenichi Nomoto in the 1980s, but remained unconfirmed for decades. In 2021, astronomers announced that SN2018ZD appears to be the first definitive example, matching theoretical predictions for progenitor type, chemical composition, and explosion energy. The super asymptotic giant branch stars that produce these events occupy a crucial gap in stellar evolution. Hypernovae are the monsters of the supernova world, releasing roughly 100 times more energy than typical core collapse explosions at around 10 to the 53rd ergs. These catastrophic events require extremely massive stars exceeding 30 to 40 solar masses, with cores rotating near breakup speed. The rapid rotation fundamentally changes the collapse dynamics, causing the core to form a black hole surrounded by an accretion disk, rather than a simple implosion. Material falling into the black hole releases tremendous energy that drives relativistic jets punching through the star's poles at 99.9% the speed of light. These jets power long-duration gamma-ray bursts, lasting from 2 seconds to several minutes, creating beams of radiation so intense they're visible across the observable universe. The term collapsar describes this mechanism, where the collapse itself creates the conditions for the extreme energy release. The explosion is highly asymmetric, with most energy concentrated along the rotation axis. Hypernovae may be responsible for some of the universe's heaviest elements and represent the most violent stellar deaths short of complete disruption. Superluminous supernova. Superluminous supernovae, or SLSNE, are the universe's most brilliant stellar explosions, reaching peak brightness 10 to 100 times greater than normal supernova. At their brightest, these cosmic lighthouses achieve luminosities from 100 billion to 1 trillion times the sun's output, briefly outshining entire galaxies. They're extraordinarily rare, occurring only about once per 10,000 supernovae, and are typically found in small, metal-poor galaxies. Astronomers divide them into 3 subtypes: SLSN1 without hydrogen, SLSN2 with hydrogen, and SLSNR powered by radioactive decay. The first examples were discovered around 2006 to 2007, and scientists still debate their power sources. Leading theories include energy from a rapidly spinning magnetar, pair instability explosions in supermassive stars, or intense interaction with circumstellar material. These events rise to peak brightness over 30 to 50 days and fade over months, maintaining extreme luminosity throughout. Their existence challenges our understanding of stellar death, and their extreme brightness makes them potential tools for studying the early universe, where traditional supernovae are too faint to detect. Pair instability supernova. Pair instability supernovae represent a theoretical class of explosions that completely destroy stars weighing 130 to 250 solar masses, leaving absolutely no remnant behind. These can only occur in extremely massive, low metallicity stars where core temperatures exceed 1 billion Kelvin. At these extreme temperatures, photons become so energetic they spontaneously create electron-positron pairs, a quantum mechanical process that removes pressure support from the core. This triggers runaway thermonuclear fusion of the entire star, detonating it in a symmetric explosion far more powerful than normal core collapse. The entire stellar mass gets converted to kinetic energy and unusual chemical signatures, including excessive nickel-56 production. Such massive stars probably only existed in the early universe as population 3 first-generation stars, or in rare metal-poor environments today. Despite decades of searching, astronomers have never definitively observed one, though SN 2007b I remains a candidate. The lack of confirmed observations suggests either these stars are extremely rare or the mass range predictions need refinement. If they exist, they would be spectacular, possibly visible across most of the observable universe. Failed supernova. Failed supernova represent the universe's ultimate anticlimax, where massive stars simply disappear without exploding. Estimates suggest that 10 to 30% of massive stars in the range of 18 to 25 solar masses experience this fate. What happens is the core collapses normally, but the shockwave that should drive the explosion stalls before reaching the stellar surface. Most or all of the star's material falls back into the newborn black hole, and the star just vanishes from the sky. There might be a brief optical transient or nothing visible at all. The best candidate is N6946-BH1, a 25 solar mass star that underwent a weak brightening in 2009, then disappeared, presumably leaving behind a black hole. These events are incredibly difficult to detect because you're essentially looking for something that didn't happen, a star that should have exploded but didn't. Failed supernovae have profound implications for understanding black hole formation, the explosion mechanism itself, and why some stars successfully explode while others fail. They also affect estimates of supernova rates and heavy element production in the universe. Kilonovae aren't technically supernovae at all, but result from the collision of two neutron stars, or a neutron star and black hole. The name comes from their brightness, roughly 1,000 times brighter than a classical nova, but 1,000 times dimmer than a supernova. When neutron stars merge, they eject neutron-rich material that undergoes rapid neutron capture, creating heavy elements like gold, platinum, and uranium. The first kilonova observed with both gravitational waves and light was GW 170817 in August 2017, detected by LIGO and telescopes worldwide. This single event produced approximately 1 Earth mass of gold and platinum, confirming that Kilonovae are the primary factories for elements heavier than iron. The explosion shows a distinctive color evolution, starting blue, then shifting to red as lanthanides form in the ejecta. Peak brightness reaches around 10 to the 41st ergs per second, and these events are associated with short gamma-ray bursts. The detection of gravitational waves combined with electromagnetic observations opened a new era of multi-messenger astronomy, letting us study cosmic collisions in unprecedented detail. If you want to see more, click the video on screen now.